Okay, well, hi everyone, and thanks for this kind introduction, and thank you for inviting me here. My name is Gkatzelis. I'm working at Forster in Germany, and today I will present to you the results of a review we performed to identify the global impacts of COVID-19 lockdowns on urban air quality. I want to start by thanking all co-authors of this work that you see here, their names and pictures. The pie on the right that you see is just for awareness and indicates the number of male and female scientists that contributed to this work. It is one of the few cases where we have an actual 50-50 split, which is great. Usually the split is dominated by male scientists, at least in many publications I've been involved in so far. But what is also great about this work is that it was a collaborative project between 3 governmental institutions, KNMI in the Netherlands, NOAA in the US, and Forster in Germany. So I will start from, things we've all seen through the last 2 years that I'm depicting here. So there's a lot of articles out there, and I have articles from the most famous English newspapers around the world that discussed during the lockdowns and during the pandemic how air quality improved substantially for specific regions around the world. This is further highlighted in these pictures you see on the left, where you have specifically pictures here of India and New Delhi. On top, you have pictures during November and October of 2019, so before the lockdowns. And below, you have pictures during April, when the lockdowns were quite severe. And you can see that, in the first case, you have a lot of traffic and you have a lot of clear pollution occurring. While on the other case, you have clear skies and no traffic whatsoever. Although there's, this already indicates that there is indeed a change in pollution during this period. There's a change of emissions from traffic, but nevertheless, when atmospheric scientists see this type of picture, they often question right away whether this is a trend that is triggered by meteorology more than emissions, because you might have less wind in the first case and an accumulation of pollutants. And in the other case, you might have strong winds that dilute your pollution away. So it's really important to, identify and the complexity of the system we're trying to look. And I have here this image that we generated for this paper that kind of shows this overall view of the complexity of our atmosphere. I will start from the bottom here, which indicates all the different emission sources of different pollutants that we have on a global scale. So you can have urban emissions, industrial emissions, residential emissions from traffic, so the mobile, but also emissions from biomass burning, biogenics, and agriculture. Many of these emissions we know drastically changed during these lockdowns. And the one that we certainly know changed is mobile sources, so really traffic, as I showed in the previous picture, as well as industrial emissions we know were reduced. But nevertheless, there's many factors here, many emission sources that we do not have a great understanding of the changes they had during these lockdown periods. Nevertheless, you have all these primary pollutants that are emitted in the atmosphere, and their concentrations are now dependent on all these different parameters that are meteorologically driven. So you have your winds, you have your boundary layer height, you have the solar radiation, the cloud coverage, the cloud scavenging, and the wet deposition that happen in parallel to change the actual concentrations of the observed pollutants. And on top of that, you have atmospheric chemistry that's kicking in. And atmospheric chemistry gives you these nonlinear chemical reactions that produce secondary pollutants. And the ones I have here highlighted are ozone and PM2.5. PM2.5 is particulate matter smaller than 2.5 micrometers. Those two are the most important pollutants to understand in terms of the impacts pollution has on our health and the air we breathe. Nevertheless, this whole complex system now we try to understand by using, measurements that we've managed to obtain around the world. So we have satellite measurements, so remote sensing like TROPOMI and OMI, satellites that really measure pollutants on a global scale. But we also have very specific ground monitoring stations, so ground-based measurements to understand changes of pollutants around the world. And of course, these two systems of information we combine to be able to inform emission inventories that are then used to initiate 3D modeling and see what the impacts of, changes of emission patterns may be when we're trying to understand this complex system. Going back to this, many of these pictures that we see during this period of, lockdown and before and after, I have again a characteristic example where we see that before we had a ton of traffic. After and during the lockdowns, we really had significant reductions in traffic. But the question is, how much are we expecting transportation to contribute to the overall emissions on a global scale? So how important is transportation on a global scale? In order to answer this, we used inventory-based business as usual emission scenario. So what would happen if the emissions, stayed as what we're used to around the world? So the map you see here is colored by the dominant NOx emission sources. So NOx indicates nitrogen oxides. So those are emissions that are coming from the tailpipe of the cars and in general from combustion processes. So what you see here is that around the world, and especially on the Western world, you see that traffic and transportation is the dominant source of NOx emissions. And on the Eastern world, it's mostly related to energy and manufacturing. And you can see that there's a few points in the world that, industrial and other processes play a role. And there's some contribution also from the pie charts you see related to buildings and miscellaneous emission sources. But overall, when you're looking on a global scale, you see that NOx emissions are, on average, 36%, and they have deviations that range from 15 to 51%. So we did the same analysis for also PM2.5. So this is the pie charts now you see at the outer box. And I don't want you to focus specifically on each one by one, but what you overall see, the overall trend we see on a global scale, and also from the pie charts I have here, is that PM2.5 is related to transportation is quite less. So it's around 8% on a global scale and ranging from 3 to 20% on average. And of course, we did the same now for carbon monoxide, which is also a pollutant that mostly comes from combustion. And we see that, on a global scale, we have 30% on average. That ranges now quite a bit more, from 5% all the way up to 70%. But what I want you to keep out of this is that overall, based on the business as usual scenarios and the knowledge we already have, we're expecting that NO2 emissions will be the most affected by these lockdown measures because traffic was reduced, followed by CO, followed by PM2.5. So we have a good understanding of what to expect, but we still need a parameter that gives us an understanding of when the lockdowns happen and how severe these lockdowns were. So what we found is this parameter called the Stringency index, which we used as a metric for lockdown measures. So the Stringency index ranges from 0 to 100, with 100 being the most strict conditions that you may have. And it includes many different parameters that can affect directly emissions or also cannot. And this includes, the implementation and extent of school closures, workplace closures, restrictions of public events, gatherings, closure of public transportation, et cetera, et cetera. So there's many parameters that are accounted here for you to be able to derive this value. And I have here a small video that shows what happened in the world, where you see that, this lockdowns happen in Asia, in China specifically, and then they spread through the whole world. And you see that in April, you have really the most severe lockdown measures on a global basis. And then as you move to the summer, you have these lockdown measures loosening up for specific countries and changing depending on the time period we're looking at. But overall, one of the messages I want to stick to from this animation is that on April, that we had the most severe lockdown measures. And because we did have the most severe lockdown measures, we did our own a bit of analysis to see, what's happening during these periods. So at the bottom, what you see is the Stringency index graph for the whole world during April. So the average Stringency index during April for the whole world. And you, as I mentioned before, you see that, the most strict conditions indeed exist during this month. And what we did is our own analysis with the help of Anna and Henk, using Tropomi data and correcting also for what changes in weather conditions that I will go through also later in this talk. But what you see here in this map is that in general, you don't have severe changes when you're looking on a global scale, but you really see some blue hotspots, let's say, indicating rapid decreases. What I did here on the top is really zoom into specific countries and specific regions around the world to show that, during these periods of severe lockdowns, you do have in urban, especially in urban environments, a clear decrease of NO2 emissions during the period of the lockdown. So indeed, based on the statistics we're looking at, we are expecting a change that we also observe from these data sets. But of course, the focus here today will not be on our own approach on this work, but the review we did for all these papers that were already published within the first year. So what I have here is a graph that shows the year 2020 until October. And on the y-axis, you have the cumulative number of papers. So in the solid line, you see the actual accepted papers and the date of acceptance. And in the dashed line, you see the date of submission of the papers. And we did review 150 papers and digitized actually 150 papers. We reviewed more than 200 papers and were able to actually digitize 150 of them, as you see here. From all these papers, you see that they were, related to different regions of the world, with a lot of publications related to changes of air quality in East Asia, as well as South Asia, but also many studies in Europe and South and North America. What you see here as a vertical line now is the time when the first lockdown started for each of the different regions around the world. So first comes East Asia, and specifically China. Moving then, you have Europe, you have West Asia, North and South America, and South Asia. What is also depicted here in red is the time when World Health Organization, WHO, declared COVID-19 as a pandemic. And even before then, we already had a first paper that was accepted for publication that actually focused on the impacts of lockdowns on urban air quality. What I mentioned here is that we tried digitizing these 150 papers. And we did that by focusing on specific measures. So I have those now here on the left. So we either identified what type of data type they used. So whether it was satellite measurements, whether it was ground-based monitoring stations that they used, or whether it was both. And you see that for most studies, so 100 from the 150, you had really the use of ground-based monitoring stations, which already highlights the importance of continuing to have those type of monitoring stations in the future. And of course, what we also did that is important, and I mentioned earlier, is try to identify which studies accounted for the effects of meteorology and which did not. And what we saw is that a large fraction of the studies, actually nearly 2/3, either did not discuss meteorology or did not quantify the effects of meteorology. And only 1/3 that included observation studies corrected for meteorology, but also modeling studies that by definition correct for meteorology, given that they run a model that is restricted in terms of meteorological conditions. But nevertheless, so this whole data set of 150 publications, we tried using it to understand, the broad changes of pollutant concentrations during the lockdowns compared to a reference period. And this you actually see here now. So these are complicated figures. I will go through them with you. On the x-axis, you have the observed changes as percentage difference. So this means the change from the lockdown to the reference period. So when you have values that are in this orange shaded area, this means that you had reductions because of the lockdowns. And when you see values in the white range background, you had increases of pollutant concentrations. On the y-axis, you have the different regions of the world. And in brackets, you have the number of publications and the number of data sets used for each of the violin plots that I'm actually showing here. The markers, the blue markers indicate the median values based on all these measurements. The gray data points indicate the different individual and data sets. And the blue shaded area indicates distribution of data during these periods. So as you already see, for NO2, you have a lot of measurements. So we have a lot of statistics for NO2 during these periods. And you see that it was actually drastically reduced with median values ranging from 20 all the way up to 60% for most of the regions we're looking at here. For PM2.5 now at the bottom left, you see that we also have quite a bit of statistics, but the reductions were less. So they range from, values close to 0 to 10% all the way up to 40%. NOx and PM10 showed the same trends as NO2 and PM2.5 respectively, but we do not have yet enough statistics to support, with confidence that these are the trends we expect on a global scale. CO that you see at the upper right here, we have enough data sets to see that, we have a decrease that is more strong than PM2.5 and less strong than NO2, ranging now from 10 all the way to 40 and 50%. Interestingly, ozone, that is a secondary pollutant, was the only pollutant that actually increased during this period for most of the regions we are actually trying to look into. Of course, we not only look on the 6 pollutants, we looked on more, and here you have 6 more. I have SO2, ammonia. This stands for non-methane volatile organic compounds. I will call it from now on VOCs. Aerosol optical depth, black carbon, and air quality index. And what you already see here is that, we either have very sparse data, at least until the time of the review of the papers, which was in October, or no data sets at all. And for SO2, where we have a few data sets, you see that the results are really sparse, ranging from minus 80% reductions to 80% increases during these periods, which indicates that there's a lot of complexity in trying to understand this type of pollution sources. But overall, from these graphs and the previous ones from the previous slide, you have trends that are actually showing a specific variability. And as I mentioned before, here we used all the different publications that show that either corrected for meteorology or did not. So the question that comes in is, what are the drivers of observed variability we have here, and how much can they affect the system we're looking at? So we try to highlight this by showing this percent changes versus the stringency index that I showed earlier. So on the x-axis, you have the stringency index, and I will remind you that as it increases, you have more strict lockdown, so you're expecting more reduction of emissions. And on the y-axis, you have the percent change from the lockdown to the reference period. So on the top, we have now all the studies that actually accounted for the effects of meteorology, and on the bottom, we have the studies that did adjust the direct comparison. What's really nice to see is that for studies that did account for the effects of meteorology, you see a clear trend of reductions of NO2 as you move to more strict lockdown measures. Same goes for PM2.5, and you also see a slight increase of ozone moving to more strict conditions. On the other hand, when you're looking on the direct comparison studies, you see that this trend ceases to exist. You have more of a bulk values that range within the same range, and no trend is evident anymore. And we tried using this graph here in this paper really to emphasize the importance of accounting for the effects of meteorology, especially when you're trying to understand percent changes of pollutant concentrations. But of course, we didn't stop there. We tried also comparing the results we have from all these different studies now to inventory emission reductions that we were able to obtain from a publication from Forster et al. In Nature that was published in 2020. So what you see on the y-axis here is our observed percent changes, so decreases, and on the x-axis you see the inventory emission reductions as a percent change too. And you see, so the dashed line here is the 1-to-1 line, and the orange shaded area indicates the 2-to-1 lines and 1-to-2 lines. What we see is that, on average, when you bin the data sets, you see that you have a very good agreement between the observations on a global scale and the inventory values, which gives us a lot of confidence in terms of how well we understand NO2 reductions during these periods, but in general also how well we understand NO2 reductions and where they originate from in urban environments. What's really interesting to see is that during the periods where you have, strict conditions, reductions of NO2, you have a logarithmic increase now of ozone that is a secondary pollutant that is also carcinogenic. And of course, this happens because you have less NOx emissions, so less titration of ozone, and therefore more ozone during the periods we looked into. Ozone, though, is a bit more complicated, and I will come back to this, because ozone is a product of photochemistry. The periods we were looking at here were mostly during the winter time, where you're expecting ozone to be low and photochemistry to be low. So titration from NOx emissions is probably affecting strongly ozone formation here when compared to photochemically active seasons like summer. We did the same comparison of our observations to the inventory from Forster et al. Also for PM2.5 that you see on the left, and SO2 that is a precursor for PM2.5 secondary pollution. So SO2 can be a product, can be due to photochemistry. Due to photochemistry, SO2 can really produce PM2.5, and it's important to understand both in terms of understanding changes in PM. But what you see here on the left is that your observed changes did not anymore show these clear trends to the inventory values, and were sparse and not really showing a clear correlation with the inventory. And that's of course because PM2.5 is more complicated. PM2.5 can originate from direct emissions from anthropogenic sectors, so primary sources, but it can also be a product of secondary chemistry and the so-called secondary organic aerosol, sulfate, nitrate, etc. So there's a lot of composition within PM that can really be secondary and really hard to identify changes of during these periods. But nevertheless, when it comes to understanding precursors like SO2 for PM, you see that we're doing an even worse job there. So the inventory and the observed changes really are sparse and are all over the place. So for such an important pollutant, it clearly shows that we need to do a better job in terms of identifying more precisely what the changes of SO2 were that are predominantly related also to, in many cases, industrial emissions. But coming back now to, I've shown you so far percent changes, right? But it's important to also understand what the concentrations of these pollutants were during the lockdown periods and also during the reference periods that we try to compare. So what you see here are, again, the different regions of the world, and in brackets, the number of publications, number of data sets. And now what you have in circle markers is the actual concentration of NO2, PM2.5, and ozone during the lockdown period. And the banded squares indicate the concentrations during the reference periods. What you have as vertical lines also here are the WHO guideline values for 1 year average concentration of NO2 and 1 hour average concentration of NO2. And when you're looking at NO2, you already see that in terms of concentration of absolute concentrations, we're actually below even the 1 year guideline values the WHO provides, which is good news because, it seems that we're reaching the values we should be. I will mention here that the WHO guidelines changed this year and are quite a bit lower. But nevertheless, even for the lower values, we're still in a range that, we might have exceedances, but overall NO2 is below these guidelines. On the other hand, PM2.5 is definitely not. So what you see here is, the 1 year and 24-hour guideline values. And for our data sets that are averaged through weeks, you see that they're clearly exceeding, actually, the PM2.5 thresholds and the guideline values, especially in Asian countries. And when you're accounting for the new guideline values that the WHO has now, even for Europe, you see that the guidelines are definitely exceeded during periods where you have really traffic reduced. And it shows that, we need to further look into this. And I will go through this in the later slides today. Finally, when you're looking at ozone, as I said, it's the only pollutant that actually increased. But as you see, the 8-hour maximum is not reached because we're not in photochemically active seasons. We're not in periods when ozone is expected to be high because most of the measurements you see here are during the winter. So as I mentioned, PM2.5 and ozone those are the two pollutants that can be secondary, and those are the two pollutants that really affect our health. And I will try in the following to focus a bit more on those two. On the left, you have the chemical composition of PM2.5 that, as I mentioned earlier, can be primary, so directly emitted by us, or secondary, so formed from atmospheric chemistry and from precursor compounds like SO2 that we've seen before, ammonia, NOx, and non-methane volatile organic compounds, the VOCs. And on the right, you see, how complex the ozone can get when you're looking at photochemically active seasons, which is depicted by this well-known ozone isoplex in our field, where you have this dependence on how much ozone you will produce relating to the amount of NOx you have, but also the amount of VOCs you have. So the more VOCs and NOx you have, the more ozone you get, but there's regions within these isoplex where you can be more sensitive to NOx in terms of producing a lot of ozone, or more sensitive to VOCs in terms of reducing a lot of ozone. So it will be really interesting to dive into these details and try to understand what's happening. And I will start from PM pollution and how well we understand the chemical composition of PM2.5 from the studies we already have here. So I have here this study that was published in Science from Lee et al. From the Caltech group that shows something really interesting. So what they found during the period of lockdowns in China was that even during that period, PM2.5 did not just decrease, it even increased during this period. So even though you have lockdowns, even though you have traffic reduced substantially, you still have PM2.5 exceeding your expectations based on 2019 and when comparing the two data sets. And what they find is that the reason this happens is because PM2.5 is predominantly related to secondary sources. So it's really not so much related to the primary, as we've seen also from the EDGAR inventory. Transportation could be 10% of the total PM, but it's also significantly contributing, secondary pollution is significantly contributing to PM. And this is not something that is actually new, especially for China, where there's a lot of publications that show that the dominant part of the pie is really related to secondary pollutants. And on the right, we have a publication that we published this year in GRL, where we show exactly this, that, around 70, and in other studies, 80% and more is secondary pollution. So if you want to understand changes in PM2.5 in the future, you really need to start focusing on the secondary pollutants, which means really start focusing on the actual primary precursor compounds and VOCs that may influence what we're looking at here. And since I'm, predominantly interested in understanding the changes in VOCs, those VOCs will be responsible for what you see here in green, which is the anthropogenic secondary organic aerosol, but also in dark green, which is the biogenic secondary organic aerosol. So what we've shown in this publication that is published this year from Nault et al. Is that secondary PM represented significant fraction of the PM mass. And what we've also found is that this part of the pie is really the reason why you have also all these health impacts that happen in urban environments. So this anthropogenic SOA will be very interesting to further understand if you want to understand impacts to health in future studies. And as I mentioned earlier, we're not doing a good job, as you see on the left, in terms of meeting the WHO guideline values. And when it comes to how well we understand the precursor compounds that actually produce secondary PM, we do not have good statistics for those. So although we have good statistics for NO2 that will be responsible for the nitrate we produce, we do not have a lot of good statistics for ammonia, SO2, or the non-methane VOCs. I will mention, since the time of the review, there's been some really cool publications related to our understanding of the changes of these pollutants. But of course, it will be great if we see more and more coming out so that we can further understand the impacts of these precursor compounds to urban pollution. I will now move a bit to the ozone story and these complex isoplex, and trying to understand the changes that we had during these lockdown periods from the VOCs. And I have here in circles what we're expecting in terms of reduction. So that air traffic was reduced, urban emissions were reduced, mobile energy was reduced. But when it comes to our understanding of industrial emissions, residential emissions, and biomass burning, we do not really understand what the impact was during these periods and whether there were reductions or not. So what I'll try doing in the following is go through a bit of the history of how important these sectors may be on our current date, and try to see how well we understand what the impacts will be during lockdown measures. And I will start, as I said, from way back in history with an image from the severe episodes in LA that happened in 1948, where many people actually died during these days. And of course, during that time, the major sources of pollution were combustion activity. So traffic and industrial emissions dominated the anthropogenic sources that contributed to this really severe pollution episode that you see there. However, we had a transition through the last years, from 96s all the way to 2010, where you have a decay of all these pollutants that are known to originate from combustion. And I will mention here that this y-axis is a logarithmic axis. So you really have a drastic decay through the last years of these pollutant concentrations in urban environments. And, in the present, when you're looking again back to how LA looks, you have 4 times less ozone than you did before, but still you're exceeding the national air quality standards, and we're still not getting a good enough air quality that's not impactful for our health. And what we found in terms of understanding how much the VOCs may impact the system is that, and that's a study from McDonald et al. That was published in Science in 2018, is that volatile chemical products emitted from indoor environments can contribute to outdoor pollution. So volatile chemical products, as I'm showing here, are products related to personal care products that we put every day, cleaning products, deodorants, adhesives, insecticides, and paints. So it's a combination of many different categories of chemicals that we use on a daily basis. And what was found for LA is that in terms of understanding the VOC emissions, these volatile chemical products that I have here as VCPs really contribute half of the emissions of VOCs when compared to what we are used to thinking that is the dominant source of VOCs in urban environments, which is exhaust from engines. And another study that came out exactly the same year from Cognitol showed that actually D5-siloxane, so this is a compound that is used really specifically for personal care and specifically for deodorants that we put every day. So even now I'm sitting here, I think I'm emitting currently D5-siloxane because of my deodorant. And what they found, so what in Cognitol is, what I found really interesting, that when you drive to work in the morning, you have benzene coming out of your tailpipe in the car, but also you have the same amount of D5-siloxane in the morning coming out of your armpits and out of the window. So when you compare D5-siloxane emission rates and benzene that's coming out of your tailpipe in the morning, they match. And as you go through the day, you have the second peak of traffic while your deodorant has already evaporated. And interestingly, what this shows is that, this source is indeed significant. We are finding here tracers that show that this type of emissions, which are residential, right, are quite kind of significant. And what we published this year in ESNT is actually a long drive we did from Boulder all the way to New York City with a mobile laboratory from NOAA. And we found that these VCP sources are significant, in cities like Boulder, where you have, so this is a population density map, and you see that Boulder is populated, but not very highly populated, but nevertheless not very densely populated, sorry. And, but you see that you still have a 50-50 split of VCPs and traffic for the compounds we actually measured here. And when you're coming to New York, that is the most populated, clearly most populated city in the US, you see that the VCPs are dominating your actual signal and the VOC emissions. And the question that comes up, those emissions are significant, but are they contributing to the overall ozone production? And a publication has been published the last month or so by Cognitol is this one, where we show that we have a significant amount of VCPs related to the actual anthropogenic VOC emissions, But what we also have is a significant production of ozone. So still, when it comes to understanding, the ozone production efficiency of these compounds, you have your traffic contributed around 60% of the anthropogenic ozone produced during this heat wave we actually observed in New York City, but 40% of that is related to these VCPs that are not well studied, and the influence of those and the change of those during the lockdown periods is not understood at all yet. Adding another complexity to understanding, these changes of ozone and what they may be impacted from. I have this graph of a wildfire on the back to show that, if you have an influence of wildfires within an urban environment, this can become quite a bit tricky. So what we showed also this year from Robinson et al. From a study we did during FireXAQ is that you see here the ln over q indicates, I will not go through the details of what this indicates, rather than say that it's an indicator of whether you produce a lot of ozone if VOCs change, or if you produce a lot of ozone when NOx changes. So what are you sensitive at? If you increase NOx and get a lot of ozone, you're NOx sensitive. If you increase VOCs and then get a lot of ozone, you're VOC sensitive. And what we found for evening and afternoon wildfires is that they transition very fast to a NOx sensitive regime. This means that when you have a plume of a wildfire that comes, that has already moved to this NOx sensitive regime and passes through an urban environment, you will have a rapid and very efficient increase of ozone in this urban environment. So when you're trying to compare the ozone during that period to a reference period before, you will get results that might not be fair, because you're not comparing apples to apples. So main message here is that we should be careful, especially for a period like last year where wildfires were massive in places like the US. We should be careful how we interpret changes in ozone. Finally, I want to spend a few slides discussing, what the changes in industry and energy were. And I will do that by focusing on the actual flights we performed in summer of 2020 using our Zeppelin in Germany. So we equipped the Zeppelin with a hatch box that had low-cost sensors and an optical particle counter. So the low-cost sensors included measurements of NO, NO2, CO, ozone. And of course, we also had a GPS for lat long and altitude. But we also equipped it with a newly developed instrument called MIRRO that has the potential to measure all the compounds that you see here on the right. So ozone, NO, NO2, CO, SO2, ammonia, water, methane, N2O, and CO2. All at the same time, all in 1 hertz, and all can fit in 1 rack. So for experimentalists, this is quite exciting, because before, for you to be able to get all these type of measurements simultaneously, you needed probably 3 racks instead of 1. But now we were able to fit, in 1 rack, all these measurements and have results that look like what you see here. So this is an overview of all the flights we did around Germany, and they're colored and sized by the ratio of NOx to CO. And this we did in order to see whether, we have clear indications of high NOx emitters around Germany. And what we were actually excited to see is that, these hotspots you see clearly coming up from these flights are predominantly, if not all, related to industrial activity. And this kind of shows also the potential of this type of measurements with the Zeppelin to be able to identify, pollution sources that may play a role in the overall NOx concentrations you see on a global scale. But I will move to this, we tried focusing on a very specific now industrial plume, and this comes from Langerwehe, which is close to in between Cologne and Aachen. So this is a coal energy production power plant. And as I mentioned, it was a painful day for the pilots, but it was actually a great day for science, because what the pilots had to manage in terms of their stomach to do is really fly around this industrial activity on a closed perimeter and on an outer perimeter, but also not only do that at specific heights, but also change heights, because the Zeppelin has this real unique ability to easily change height and predict what you are getting in different altitudes. So we did that, and we did this comparison for more than 8 hours. in order to be able to derive good analysis of what the emissions from this industrial facility were. And I have here an overview of the actual results, where we compare now the observations that you see as a line here to the actual inventory, the actual URAD model that we have available in the Folsom Center Jülich. And you see that we have a general agreement of the two, both the NOx and CO, which is great. And but the question we had, as you saw, we did this many times. And although we had an agreement in the morning, what we saw is that during the remaining day, we had really an overestimation of the emissions from the model when compared to the actual observations we had. And that's, of course, for NOx, but for CO, that is not expected to be an emission from this industry, you see that there was a very nice agreement between the model and the observations. So what got us triggered about this, NOx differences is what was the energy that was produced from the industry during that time. And we did look into that by these energy charts that exist online, where we saw that what you see here in green is the power consumption for a yearly week average. And with orange, you see the week average during the period that we actually measured. And specifically, when you're looking at the red box here, it is the actual period when we flew. And you see that during that period, the production of power was really low. And this may be due to COVID. This may be due to a higher percent of green energy production. And this is something we're further looking into. But nevertheless, we have periods for these industrial activities that drastically change in time. And it will be interesting to see how those correlate with different models in the future. So to conclude about the impact of these VOCs on the measurements we're doing, it's definitely important to identify and understand these changes for volatile chemical products in urban environments, disentangle the influence of wildfires, and of course, further understand the changes in industrial emissions. We can also affect SO2, which I haven't touched today. Moving to further on concluding remarks from the overall review here, I will highlight again the importance of accounting for meteorology when looking at this trends of change of pollutants during these periods. And of course, we have a lot of statistics for specific compounds, but we're lacking statistics on others. And it will be great if, start filling up these data sets with more information. Finally, we did comparisons to emission inventories to see that you have good agreement for NO2, but there's more work to be done for other pollutants like PM2.5 and SO2. Interestingly, we have this logarithmic ozone increase with stringency index that is evident for the winter time. It will be very interesting to see what happens in the summertime, which is also one of the future recommendations we have here. And I will start with this one, that, ozone during photochemically active seasons will be very interesting to look into, especially when you have lockdown measures implemented for specific countries. We have a lot of information on the PM2.5 concentrations, but nevertheless, it will be great if we can add some chemical speciation to this PM2.5 data in order to be able to understand the importance of primary versus secondary pollution. Finally, we included here a large number of short-lived species, but we're looking forward to including a lot more and adding more to this data sets we have. And radiative forcing associated with short-lived climate forces is a priority, of course. And I will mention and highlight that this review has been limited in scope to short-lived climate forces, but there's, of course, a lot of studies that focus on methane, CO2, N2O, and halogenated compounds that are very interesting to look into, and we're planning to also add those to future analysis. Finally, I want to highlight that we have a database, an online database that it will make us happy if you visit and look through it. And also it will make us even more happy if you submit your own data. So you have the capability of downloading the data I already showed you. You have the capability of making your own graphs for different countries around the world and different pollutants. And you also have the possibility to upload the data and results from your own paper published after the period that the review was generated. And with that, I will stop here and will be very happy to answer any questions.